Hi, good
Good afternoon,
afternoon.
everyone. Shortly, we will hear an interesting lecture by Dr. Milan Oeri and MSc Enrico Dardanis on Terahertz Time-Domain Spectroscopy. This is part of a webinar series held by Photonics Israel as a part of the engineering conference, which is organized by AEAI on various aspects of photonics. The photonics industry is a technological and economic growth engine in the world. In Israel, it contributes about 6 billion annually to the economy. Photonics Israel operates within the Engineers Association as a cluster of photonics entities. Since we started operating last year, we have established close relationship with similar clusters in the US and Europe. Our mission is to deepen the knowledge in this area and to encourage cooperation both within Israel and with photonics entities in the world. We are open to your suggestions and would love to help foster new local and international collaboration. My name is Roy, and I'm speaking on behalf of Shlomo Glazer, who is the manager of Photonics Israel. You can ask questions via Q&A during the webinar, which will be answered at the end. Milan and Enrico, the stage is yours.
Hi all together. Hi to the audience. Good afternoon. This is Milan Oeri. I'm Terahertz sales engineer at Menlo Systems. I have some backgrounds in physics. I did my PhD in the field of photoacoustic imaging and tomography and signal processing. I'm with Menlo since around 2.5 years now. Next to me there's Enrico Dardanis. He has also some roots in physics and in specific terahertz near-field spectroscopy. He is at Menlo since 2.5 years now, and he will be responsible today to give you some examples on what to do with terahertz waves and specific on some terahertz applications that you in the end are going to decide which one are the most exciting for you. The presentation today will start with a short introduction on Menlo Systems, of course, that you know this company a little better, that you know what our main expertises, and in specific, the seminar will take place on the topic of Terahertz Time-Domain broadband spectroscopy, where we will go here to show you some technical information in the beginning, give you a fundamental understanding on how to produce and how to detect terahertz waves. And of course, in the end, you will be excited, I guess, to see a system live running and doing some test measurements in the end. The last quarter of this 1 hour today is dedicated to you. So please, whenever you have any questions, you can collect them already in the Q&A where you can put your questions, and we will be pleased to answer this, whether it's going to be in this presentation right away or in the end where we reserve you this 15 minutes. I'll start by my presentation by mentioning a few words on Menlo Systems. Our company is based in the very southwest of Munich, as you can maybe see from the background of our screen. This is the famous Frauenkirche in the center of Munich, and under good weather conditions, you can see the Alps from here. So it's a beautiful location here. It was founded 2001 as a spin-off of the Max Planck Institute for Quantum Optics. Two of the company leaders did the PhD under the later awarded Professor Theodor Hensch, who has been Nobel Prize awarded by the invention of the frequency comms. Under this development, frequency comms have been developed using fiber technology lasers, which is one of our core components. If you follow this first line here, the 3 main core components that Menlo Systems is offering is frequency comms, femtosecond fiber lasers that are part of frequency comms and also part of Terahertz time-domain spectroscopy systems, which is the main topic today. Apart from that, Menlo Systems holds around 130 employees right now, out of which a good third holds a PhD degree. Most of them are from the field of engineering and physics. Menlo Systems also owns a worldwide network of distributors and partners, to mention just 2 very famous ones among them. It's Thorlabs, one of our co-founders, and our strategic partner who recently joined the company, Hamamatsu, Japan. So all in all, we can look back to a continued growth over 20 years, almost 20 years now. And this is can also be followed by our continuously added value to our product portfolio, which ranges from femtosecond fiber lasers, frequency comms, terahertz spectrometers, but also timing system, not only dedicated for the scientific community, but also for the industrial market. So as you see on this slide here, our 3 main components are shown here from left to right. We have the femtosecond fiber lasers, a core component of most of the systems to the right, the terahertz systems, and the frequency comms. You might wonder where you use fiber second and in specific femtosecond fiber lasers. To mention a few markets, you see it on the left figure. It's the biophotonics. It's of course the terahertz spectroscopy region, but it's also metrology reasons, test and measurements, and also material processing and 3D printing in specific. Our customers, as I said, are from each part of the university, research industries, but also really national laboratories and industry markets. Now this is the time where I'm supposed to show you a live demo of a system, and this I can do because the system is so small. So basically, as you will know later, this is one of the core components by which you can also generate and detect terahertz waves, one of the fundamental sources you would need. I can plug this oscillator. So basically, you must imagine this is a laser source. Some know them from the labs. Some are a little bigger, like Titan Sapphire lasers. Well, this one is a 1560 nanometer based laser source. We call this laser source erbium based laser sources. And it gives you short pulses in around 60 to 100 femtoseconds. So all is fiber inside this laser head here. And what is nice about this laser head, it's so compact, it's all fiber, and the fibers are even glued inside. There are no movable parts or no satchable absorbers, as you would see it from other suppliers, which makes the system so robust. So I can plug this battery solar station to the laser source, and each laser from us comes with a certain LED light that shows the mode locking status of such a laser system. Mode locking status is a fundamental condition which enables the laser to be in operation. So don't worry, it's not the laser output, but it will be the LED that flags off here. And if I turn on this battery station, it flags from reddish, bluish to something in a green regular heartbeat. And once this is achieved, the laser is ready for operation. Even if I knock on the laser, it keeps the mode locked, which is shown by the green light. So to show you this, I have to mention that this laser source is one of the core components of most of our systems that we provide. Similar laser systems, similar technology are also being used for our core component, which is the frequency comb. You might wonder, what may a frequency comb be good for? A frequency comb can be, on a high level, very easily explained as a ruler to measure laser frequencies up to a very precise digit, which is not available by simple electronic means. In specific, applications include optical clocks or airborne gas monitoring, where our lasers are being operated in a controlled manner. To give you just a few numbers, what precision we are talking about. We can achieve a precision or accuracy of the system to define a laser frequency up to the 18th digit of the comma in just 120 seconds. And the stability to define this precision is given as 5 times 10 to the minus 18 in just 1 second. To compare these scales, so this is equivalent to an error of less than 1 second since the Big Bang. So this is really a tremendous result. Okay, now let's come to the main topic today. We are talking about terahertz. Terahertz is an energy gap that is so far not addressed so easily. You well know the electronics and the photonic side. There are different ways of how to achieve and how to address the terahertz band gap, which is around 1 to say 10 terahertz in the normal definition. There are many applications that you are well familiar with, either from microphone or microwaves or from the infrared. You know the visible part, the ultraviolet or X-rays in the higher frequency range. Let us have a look on the application, what terahertz can be helpful to. You see some examples given here. Let me say these are not all the examples, but one of the more sophisticated and one of the most frequently used. So we have the pharmacy on one side, something like a monitor processing where you can, by spectroscopic footprints, differentiate between different tablets and do the controlled steps by terahertz. We have the safety side to differentiate different liquids, for instance, for a security check on airports. We have the non-destructive testing field, as also referred to as NDT, for instance, on the painting layer control of cars. And we have material sciences, one of the main application fields, and of course the optics. Not to mention also the biosensing part. So Enrico will type in a few seconds some of the applications that you are freely able to choose between. In the end, we will prepare, depending on the time left, around 3 applications. So please look at the chat window, and in between we will have some time to set up this information where you are free to choose. Let's have a look on how to generate and detect terahertz waves the classical ways. So there's different ways on how to address the terahertz gap, as I said, coming from the higher frequency part or coming from the lower frequency part. The first slide shows the first case coming from the photonics or the optics side. Here you could either use a femtosecond fiber or a femtosecond laser, ultra short pulse laser, or an optical beat by 2 continuous wave laser sources. There are different ways on how to generate terahertz. You can use either a crystal which will be excited by the optical pulse, and by optical rectification you are creating electron terahertz waves. Or nowadays, most likely and the most flexible way on how to do this is to use photoconductive switches, so semiconductor antennas. In the first case, using short pulses, broadband pulses, you will get a broadband terahertz spectrum. This is one of the main differences between the broadband terahertz, or also called time-domain spectroscopy, or CW terahertz spectroscopy. I'll not go into much detail for this part, but our part will concentrate on the upper part here. But on a side note, let me add the second option to come from the lower frequency end part, from the electronics part. And this you can do by using microwaves and applying a diode, which enables you again to get continuous wave terahertz waves. This talk will be about this first part, using a femtosecond pulse, using photoconductor switches, and operating it into high broadband terahertz spectroscopy. Let's have a more closer look on how we create terahertz waves at Menlo systems, and in specific some of the parts you will see for all applications and all cases how to then generate and detect terahertz. But one of the most important features here is, on the first hand, the ultra-fast laser. So this is the laser source I had in the hand before. Typically, such a fiber laser comes fiber coupled with 2 output ports. One is going to the emission side, a second one is going to the detection. Now, if you want to sample a terahertz signal at different timestamps, because the technology itself is a time-resolved measurement, you would use for one branch a certain time delay. There are different ways on how to address such a time delay. A very conventional and most precise way as of to date is to use an optical delay line. And this is what's shown here. So basically, this is a linear motor stage where you would have certain reflectors on the back end and it moves back and forth. While I was saying that the full systems that we from Menlo systems offer are fiber coupled, let me add this on a side note. This is the only tiny space where there's a free space application of the full system. So if this linear stage moves back and forth, you can imagine these optical pulses. If both fibers have the same length, they sample a terahertz signal at slightly different timestamps. Now let us have a look on the third very important component. It's the emitter or the detector side. This is the semiconductor material I was mentioning. Enrico, you might in between start offering the different applications, and I continue with my talk right away. So on the right side on this figure, you see the scheme how to generate and detect terahertz waves. First of all, we use semiconductor materials. An incoming optical pulse that's shown in a reddish color hits the semiconductor material in a very defined and precise mode. This excites electron and hole pairs. So we are creating electron and hole pairs. In addition to that, we apply a certain bias voltage to the semiconductor material. In turn, the bias voltage accelerates the electrons through pairs, which enables to produce terahertz waves. This is all on a controlled optical excitation. Now, since we created terahertz waves, we have to deal with it. And here at Menlo, we are using either polymer lenses or parabolic mirrors, depending on the configuration and the needs of your experiment. So what you see in the yellow color over there is the terahertz path. We are using polymer lenses, less sensitive than classical optics as you know it, but we use them for collimation and focusing of the terahertz path, for instance. So this in the center, I have to use my, let's see, the pointer. So this is the center where we typically place the sample. In this case, it shows a pinhole. A pinhole is being used to do the fine alignment of the terahertz path in the end. Of course, you are free to adjust all these spaces in here. So this depends really on your experiment. You could use different focal lengths and different settings. You can even go into reflection. So this is just showing the transmission path here. Now on the detection side, we use actually the same principle as for terahertz generation. Now here, the incoming terahertz wave is replacing the bias voltage because it accelerates the electron through the holes. Again, we are creating those electrons in hole pairs by optical excitation. Now, what you measure here is the photocurrent. You amplify the photocurrent measured, no need for log-in amplification. Signal-to-noise ratio of photoconductive antennas is much higher than you know it from earlier days, maybe. And then, of course, we AD convert it and compute it in the PC. Let me go to the next slide, Enrico. So this scheme shows the sampling scheme again. We have the femtosecond laser source. We have two pulses outcoming, whether it's fiber coupled or not. We have a delay stage over here. If I move it back and forth, I can sample different stems of the time resolved measurement of the terahertz signal itself. Now by Fourier transform, we can analyze the spectroscopic footprint of such a system. Again, I have to explain. The nature of such a system is to give you a time-resolved signal. So this you will get by hardware and per definition. By computational means, you can get the spectrum of your analyzed data. And here's a typical example which you can use, which shows some nice footprints, which we will also show you later on. You typically measure a reference signal, then you compare it to the sample. So you're just replacing plain air by your sample. You see a certain decline in the amplitude, and you might also observe certain phase shifts due to changes in the refractive index of the material. And this is the clue of the Terahertz Time-Domain spectroscopy system. You could use this either to look at the spectroscopic footprints as given here compared to a reference, or you could use it to measure thicknesses of a sample in the time domain, which you will observe by certain changes in the time domain. Or you can use it to analyze a sample by calculating the refractive index of your material. So this is what's shown below. We have the absorption shown here and the refractive index here, which can be derived from a single measurement from a more or less single shot from such a laser source, which creates broadband terahertz spectroscopic data. Now, dealing with time-domain spectroscopy, there are different ways which address different regions of the applications. And here at Menlo, ours include three different systems. One's more dedicated to OEM customers, customers or students who work with the system, don't need to have much access to it, or plain terahertz time-domain spectroscopy applications. From left to right, we have the TerraSmart over here, that's the compact one. This system includes such a laser system, a PC, everything is integrated nicely into a 19-inch rack box. And you have, of course, the terahertz path that gives you certain flexibility, of course, because the fibers can be delayed in a length that you desire. In the middle, we have the TERA K15. I call this the multi-talent at Menlo system because it adds a certain value in terms of the optical part of the system. As you know, we use a femtosecond fiber laser for creating electron for terahertz generation detection, but you could use the same laser for optical excitation of your material. And this is what TERA K15 stands for. And then, in contrast to the first two ones, which are using the optical delay line, as I explained to you earlier, we have a third model. As you can see it from this picture here, it uses two lasers that are, however, locked to each other, but with a well-defined manner in the repetition, well-defined difference in the repetition rate. So it's one characteristic of such a laser system is the repetition rate, how often you fire a pulse in a certain time interval. If you control these repetition rate differences nicely, it adds up until a second pulse hits the first pulse again. This means you can use a much faster scan rates and achieve a much higher spectral resolution because there's an inverse relation between the length of your scan path and the tiniest spectral resolution you can get out of your system. Let's have a look on the first system again. As I said, the compact laser source is inside this laser system. It's a turnkey system. It comes with software, all the hardware and electronics that you would need to do terahertz spectroscopy. There are two values that I like to share with you. One is the dynamic range. This is one of the key parameters. Basically, it's nothing else than the signal to noise ratio. And on the other hand, it's the bandwidth of such a system. So how many terahertz can I measure? In contrast to the first system, we have a different fiber laser source here. A fiber laser source that's much more sophisticated, which offers you to do optical pump terahertz probe experiment, which can be even synchronized to synchrotrons outside of the terahertz spectrometer, which, to keep it short, give you much more flexibility for such a system. Looking on the terahertz path, we introduced a new terahertz path, not using polymer lenses anymore, because simply the detector, the emitter, terahertz emitter, delivers much higher bandwidth. A higher bandwidth that, on the other hand, yields a certain attenuation by polymer lenses. So we replaced the polymer lenses for this specific emitter by parabolic mirrors. And here you see the use of 4 off-axis parabolic mirrors, 2 for focusing. You have the plug-in detector, plug-in emitter on that side. You have the collimated part, and again, the focus part where you place a sample. In our case, here we have a placeholder pinhole for fine alignment. The software looks similar to this shown here. So basically, as I said, it's a time resolved measurement. So this you get for free from the system. It's a time domain signal. What parameters to define this here is the amplitude and how many echoes you see after such a pulse, how nicely a pulse is shaped. You can transfer from time domain into Fourier domain by Fourier transformation. And what you then observe is this spectroscopic information of the sample here. The value that's given here just shows a reference measurement. You might be wondering why these declines or these peaks are coming from. This is basically water absorption. So if you're not familiar with terahertz yet, let me say that water is a strong absorber of terahertz. You can, of course, get rid of these peaks over here by purging your experiment. But for some experiment, it might be required to know how exact your system is. Our systems all can be remotely addressed, and you can use it basically with every modern programming language. What is nice about newer development is that you cannot operate only one emitter and one detector, but also several detectors, several emitters to make the best out of your system and to give you the most flexibility for your experiment. An example is shown here. You have one emitter, one sample, which is placed between emitter 1 and detector 1, which gives you the transmitted signal on the one hand, that's the blue signal. And at the same time, without changing your experiment, you can detect the reflected signal of the same sample and overlay it, of course, in the software in the end. I have to look into the chat room in between, see if you have some questions. Okay, this still refers to the application side. I will come back to it once we start with the application. This should be the next slides. I skipped this slide for a while. I'd like to share one information on the TERA ASOPS. So maybe you know this face sitting right next to me. That's Enrico. So he is the one who's also responsible to install or also to produce your ultra-fast systems. And as you can see from the left figure again, it's 2 laser sources slightly locked to each other, but with a well-defined difference in the repetition rate. This difference sums up such that it comes back and samples the same pulse under a certain condition. Let me explain you in more detail. We have one laser source here, second laser source here. I call this pump. The second one is probe. So you call this by definition a pump probe experiment. Each of these laser pulses has a slight delay. As you can see it here, the delay sums up and enables you to sample the same terahertz signal at different timestamps. You can do this by a certain master-master locking configuration. You have the same reference under which you lock laser B and laser A to it, and you adjust for slight delays by certain control elements here. I'm not going too much into detail as of this. And of course, if your experiment requires imaging purposes as for non-destructive testing or safety, TERA Image is an automated imaging software which enables you also to automated acquire your images, but also to analyze the data with a dedicated hyperspectral imaging platform that's called Image Lab. Now we are reaching the part for the application. Let us quickly go to this chat room again and see how you decide. So hello everybody. This is Enrico here. As Milan said, I'm application engineer here at Menlo since 2.5 years, and I would like to introduce you some applications. I prepared for you 5 or 6, but I see that so number 4 is NDT. So we have mostly spectroscopy, biosensing, and NDT, I would say. And then maybe if we have time, we can see a little word about metamaterials, I would say. So I will go away from here. So spectroscopy, that's, let's say, what I would define the classical application of Terahertz Time-Domain spectroscopy. And actually the slide was already shown. So the measurement of the electric field, of the Terahertz electric field that we perform here, it's a time resolved one. So that gives us access to also the phase of the electric field in the complete domain of the frequency spectrum. So we can not only perform a Fourier transform where we see amplitude of our electric field in frequency, but also extract the phase, and so get information on refractive index of samples. I call that a macroscopic spectroscopy experiment because I want to distinguish to the next slide where we talk about biosensing. Because here the experiment is a classical experiment. I have a slab, and I put my slab through the beam, and I take 2 measurements, like typical in spectroscopy, or people from FTIR would know that. I take a reference signal that gives me the status of my instrument, and then I put my sample inside and I compare the 2 measurements, and I can calculate and extract material parameters. So what we see here is, for example, absorption of the lactose sugar. I will show it live just in a few minutes, and the calculation of the refractive index, where in correspondence to the absorption resonance, we see a high variation of the refractive index. What you can see is water lines here. For people looking for even more precise spectroscopy, it's possible to get rid of them. Then the effort in experiments will be a little bit tough, because then you need to purge your environment with nitrogen and dry air. And about tough conditions, biomolecules is something providing you a challenge in experimentally speaking, because usually they are inside some water solution, and the quantities of biomolecules that you want to sample are very low. That's why some researchers of France, using a TERA Smart from Menlo system, they developed butterfly enhanced field enhancement structure. So it's like a metallic antenna which allows the field enhancement in very low region, so very low volume. And that allowed them to reproduce this spectrum that we see here, that was measured with a macroscopic tablet of lactose with a very small quantity of powder or liquid. So they first make a dry experiment in which they put here in the gap 200 micrograms of lactose, and this corresponds now to the black spectrum. So they were able to reproduce, let's say, the first 2, even 3 resonances of lactose, and then they tried it out with the solution. The volume of solution was only 10 microliters, and they were still able to reproduce a couple of peaks, which shows that the technique opens the way to sensing very small volumes and in very complicated situations, experimentally speaking, where a macroscopic approach like this will give you no chance. And I will move now to the next application. So there were many people asking for NDT, and we did in the past a lot at Menlo with some research partners about NDT. So of course, I will start from a very classical example. As we see that Terahertz, we know that Terahertz water present a very strong absorption in the Terahertz region. So classically in the literature is studying the humidity in a plant
as evolution of time. The technique is non-destructive because we don't need, for example, to extract the water content by burning the leaf and waiting it before and after. We can just monitor the Terahertz transmission as a function of time. So here the leaf is cut, but actually that could be done in principle on a tree if we have a measurement head to use. And speaking about water, studies on capillarity can be done. So this is a wood polymer compound in which we can study how water penetrates inside the sample by using simply Terahertz transmission. But Terahertz transmission is not only the one parameter we can analyze. For example, we can make phase images. In this NDT, the non-destructive testing of polymeric compounds, in the Terahertz region, a known property of polymer is that we can extract the density of the polymer by studying the refractive index, which means by studying the phase delay of the Terahertz wave. And here we can make a map of an injection mold part in which we shine Terahertz light on it, and we can study how the process of molding through a barrier produce regions of higher and lower density. So we see we inject from the bottom here. So we have an area of very high density here to the barrier. And then after the barrier, there is an area of low density. And here again, concentration of compound. It's something that in the visible image we cannot see, but with Terahertz can be revealed. Just studying the phase delay, for example, of the main pulse. Again, on the study of density, we can study pressed polypropylene with different area of fiber contents, or even a more fine measurement, that's a polarization result measurement. Terahertz light, the way we generate it with PCAs, with photoconductive antennas, is polarized slightly. We can polarize it more and make repolarization result measurements in which the material under examination has a birefringence. So we have a polarization orientation dependent refractive index, and that we can explore with Terahertz transmission and reproduce a map of the orientation of the fiber that's correlated one-to-one with the refractive index value, as we can see in these images. So I have not so much time before switching to the demo, so that's why I will jump to the last requested application. I think I can see the chat. It was well, spectroscopy we cover, NDT we cover, biosensing we cover. So actually I could make a word about metamaterial because we have a little bit of time. So this is again other quality control application. Thickness, I think I will jump. I just take a word on thickness. We have a reflection net for thickness measurements. People interested can have a look at the website. So metamaterials, the group of Cambridge University, also a customer from us, is very much involved with the study of metamaterials and graphene. And they recently published a work, it's last year, about a polarization control using a graphene metamaterials. They designed a metamaterial circuit where couple resonator structure is designed, and the Terahertz field excites in different polarization, different area of the structures. And by changing the voltage on the gate, they can control the conductivity of the graphene underneath. So it's all deposited on a layer of graphene. And the conductivity change, that's changing the coupling with the resonators. And they can actually shift the value of polarization. So they can decide how much of the component of the field in the X direction with respect to the Y direction is transmitted, and this just with the gate voltage. And at the resonances of the structure, they measure the modulation speed for the Terahertz polarization of 5 megahertz. That's due to the high speed of graphene. And they could rotate almost 20-degree depolarization by obtaining always a linear polarized field. So there is no elliptical polarization induced. So here details about the publication can be followed, of course. And that I would say it's all for now. And so I would like to invite you now to the TERA system live demo. It's running just away. I will change my headphones now.
Hi, can everybody hear me? Can I get a feedback?
We can hear you.
Okay, perfect. So now we are on a different screen. This one is showing the system as I explained to you earlier. I'd like to do a short introduction before Enrico takes over. I'd like to explain you what different components of such a system include. As I mentioned earlier, there's a laser source in this rack. It's sitting behind this fan. It needs no cooling apart from this fan that's cooling down the electronics and the laser a little. We have the optical delay unit over here. So basically you have access to it. This is because you want to store it safely. So once you pull the system out of your lab, put it to a different place, which is possible because this one only needs the power supply. That's the only plug you will get from external. You would need to fix the optical delay unit once such that it not moves back and forth. You don't want to have destroyed optics over here. That's the main point. Looking on the connectors here, we have the bias voltage for the emitter. We have the signal output that's feeding into the system. We have 4 ports over here. You might be wondered why there are 2 ports left open. Basically, these are the optical ports. So as you see from the color, it's the same port that's going to the antenna over here. We have the emitter over here. The detector is on the other side over here. And all the blue cables are optical cables. So this is where the excited pulse are coming out. That's the femtosecond pulse that's creating the electron and hole pairs in the semiconductor. There are 2 ports left open as shown here. So this is the option that's referred to as dual detection or multi-channel. It's not laid out from the very beginning, but you can use this port as an add-on to all our systems. Even also for TERA K15, it's not a sole feature for such a system. So basically to start such a system, I would turn on the system on the backside. I would switch on the laser source, open the graphical user interface, enable the bias voltage, and then we are ready to go. Short note on this optics here. You have seen it before. I'm not going to show you this again. Just let me quickly explain emitter and detector. We have 4 off-axis parabolic mirrors. The main point where I would put my sample is basically here. So basically we have the free space over here. We use this for the demo now. And now I'd like to hand over to Enrico in a couple of seconds again. I switch to my screen again, showing you the scan control software. Enrico might to tell you a few words on the software again, and also do the test measurements or live measurements with you.
So hi again, everybody. I hope you can hear me. So the screen we are seeing now, it's just the running scan control software. It's a very, the interface is mainly composed by these 2 plots. So on the left side, we see the real-time plotting of the time domain pulse. And on the right side is the calculation of the Fourier transformation of it. Now the measurement is running on the average mode. I am averaging 200 pulses together. It's around 20-second measurement time. I will just let you have a look at what we call the single shot pulse looks like. So the system works on a running measurement in which we do not use any lock-in amplifier. That means we just let the optical delay line run, and we acquire on the fly with a very high speed. We are speaking high speed for a mechanical stage, few tens of hertz. We acquire the signal, and to increase our dynamic range, we just average a lot of pulses together, as opposed with a lock-in amplification method where we fix ourselves in a point in the time delay and we average over that. That gives you the possibility to just see the spectrum dynamically. The software has a few features. We can save the signal, we can start and stop the linear stage like I'm doing now. We can set our scanning ranges and the number of averages we want to do. We can also hold the signal to have a look and to have it in the background. So for example, now I hold the signal right now. I will put my hand in the beam. I will see that I screen the beam, but on the background, I see my reference there, so to say. That we can use to have a feeling of spectroscopy, let's say in real time, because I will hold now my background signal, so my reference, so to say, and I will put now in the beam a lactose sample. And I will reproduce live for you right now the measurement of the lactose absorption. So you see the main absorption peaks. There is a third one that is not so well seen, but once we take the proper absorption transmission ratios and we calculate material properties, we can retrieve it. What is nice about this locking free approach is that we can see right away the spectrum we are working with. We can increase our dynamic range by averaging down. So for example, here I can put some averages on, and that will help me to see better, for example, the resonance here. And the data that I can save with the software are just time domain and Fourier transformation data. Fourier transformation will save not phase information. That's something we do later in data analysis. So our real signal is actually the time domain, and that contains all the information we need for the data analysis. We have to save, of course, reference and sample as well, and perform our spectroscopic analysis. Another example I would like to show you is just metamaterial, very simple and cheap metamaterial actually. I cannot see it, it's just there on the table. Now Milan will bring me the probe. So it is just an aluminum foil with some periodic pattern, and it's used to create a sort of bandpass filter in the Terahertz range. There are many papers on that. It's a very classical. Exactly, now I position that. So it's a bandpass filter, let's say, with 10 dB attenuation between the main band that is passing through and all the other ones. 10 dB is not extreme, but to be a very cheap aluminum foil, how it is done, that's pretty good. And we can see it here, yes, it's around 10 dB, and that's the band that is passing through. It's around 0.3 terahertz. It's depending on the geometry, of course. And more about the spectrum here. So what we are seeing, all these lines, they are our live sample always there. It's the humidity of air. And the absorption line of air humidity are always there unless we don't dry the environment. And they are for us actually a good check that our bandwidth is really as high as we specify. So when we say that we specify 6 terahertz, we also mean that we can see spectroscopic feature up to that end and mainly water lines. So it's not only a matter of noise level and signal level, it's also a level of reproducible time axis, and that we can. So water can disturb, this is what I want to mean. Water can disturb your experiment, but can also be helpful. In our case, it can be helpful to see if really the instrument is performing as we want. I've seen that there are some questions, and I can maybe, but I think we have still time, so I will just tell you more about the software. So the software has some nice feature for the users. One nice feature that I always like because it makes life simple is a find files feature. So if we just scan somewhere else, because for some reason we changed the optical path length of the Terahertz beam, then our position of the pulse is changed because it's all a timing issue. So whenever I change the position of my components here, for example, I put this antenna more far away, or I put the second mirror, so the collimated part of the beam, I make it longer. then my Terahertz light will travel more here. So my pulse from the emitter will come later to the detector. So it will be somewhere else. These are adjustments that in a scientific experiment can be done pretty often. So let's simulate a situation where I don't see my pulse. So I can go just outside the range. So from minus 425, I scan to minus 325, for example. That should be enough not to see the pulse. I will remove the old feature. I can center always all the time. So here we don't see any pulse now. What can we do? We can stop the measurement and press our find pulse feature. So the system will make a full scan and look where the pulse is, and then center again our range in a convenient 100 picosecond window with the pulse centered in a way that we have a few picosecond of zero signal that will be useful when we do later data analysis, because if we apply windows for Fourier transformation, it will allow the window here to put down the noisy signal to 0 and allow a proper Fourier transformation without features. And then the pulse comes and the tail of the pulse. From the same software, we can control the lasers. There is even a manual control. We can have a look if the condition of the laser is good enough, if the pumping current is specified. We can also turn on and off the laser by here, but actually to disable and enable the hardware, we have some buttons here, so we can switch off the antenna bias. And for a safety issue for the antenna, we can first disable the bias and then disable the lasers. But the nice thing about this software, as I said, is that everything is here integrated, even the hardware control. And all the buttons and the features that are visible in this interface, they are controllable per remote interface. That's a topic in which I was very much involved with customers. We develop an interface where we can access the instrument via a .NET QWeb channel-based interface. It's a very dynamic way of programming in which your scan control is a server that's sending signal to your application, and you can connect your client to this signal and trigger some actions. So scan control, for example, is sending all the time a signal that tells you when a pulse was measured and it's ready to be used. You can decide to attach to this signal in your client an event handler that, for example, plots the signal or makes the Fourier transform of it or saves the signal somewhere. In this way, it's an approach that's very similar to writing a graphical interface application where the user makes some actions on the button and your client has to trigger an action. And that's the same that we thought for this interface. And people are using and testing it, and they are pretty happy about it. And that can be OEM customers, or can be people with a very big lab and a lot of experiments running, and they want to integrate them in the software of their experiment. We have support for LabVIEW, we have support for MATLAB, Python, C, star, and so on, because it's a pretty general interface. So I believe, Milan, maybe we can switch to question and answer. What do you think?
Yeah. Yes, we can. I'd like to switch to my former screen now again. So Enrico, if you mind,
I will mute.
Joining me. Okay, so hello back again. We have a couple of minutes left. I ask you to ask some more questions over here. Let us have a look, and maybe I switch for my headphones, or let's see in the chat room first what questions are left open.
There's one question about...
if you can maybe I read it first. The question is, what is a typical length in analogy with coherence lens and a laser where the terahertz signal remains coherent? In a similar way, what is a typical value of time where the phase remains coherent? Okay, I need some feedback. Can you hear and see us clear?
Yes, we can.
Okay, perfect. So this is the question. You should see the question as well. Thank you for asking this. Let us revise the question for a couple of seconds.
So I believe that's mainly a question about the stability of the time axis of the terahertz signal, because if I understood well, automotive system, maybe we are referring to thickness detection. Am I right? Can maybe the person asking the question give me a feedback on that? We do have a measurement of the stability of the time axis. We did a long run measurement in which we see a correlation with temperature stability of the position of the time axis. On the short run, we measured a few femtosecond RMS of pulse drift, pulse to pulse. We have to consider that the resolution of our time axis was like point-to-point resolution, like the step size of the time axis was above, well above the drift that we measured, the pulse to pulse. For a ODU-based system, optical delay line-based system. I hope that maybe gives some insight and some answer to that question. Exactly. So that's what's I interpret the question now like time domain repeatability, but if I'm wrong, I would like to have feedback on that, of course.
Okay. Any further questions? I had one question before answered, which is actually not so easy to answer because every molecular structure is very different. What makes it helpful in the world of terahertz spectroscopy, at least this is what we figured out during speaking to customers and our R&D department, whenever the structure is more unregular and cannot be mirrored easily and has some more specific structures, it makes life easier to detect it in the spectroscopy part. Okay, thank you for accepting our answer from before. Are there any more questions? Just wait a second. I guess there's one new. Okay, so I don't know the exact application, but as I said, water is a very strong absorber. You should not measure in rain. So basically, even if you protect all the electronics, only have the open terahertz path in rain, you would see a strong absorption, and even the rain is not equally distributed over the terahertz path. So you should see reflections, absorptions. It might make your life very complex. I hope this answers your question. In any case, you're invited to go into more detail and send us your application information or your idea or how we can help you to get an answer to your ideas per email. My email address is given here. So whenever you have any open questions, feel free to answer my email address. We will be glad to look at your request. Also, Menlo Systems is offering test measurement campaigns. Even if we are uncertain if this works out for your specific applications, this is something we often do in partnerships. Our system can be even loaned whenever you are not confident the system works for you. There are many different options on how to provide you an answer to these. So I guess there are no more questions as of now, if that's the case.
Thank you very much.
I thank you very much for the invitation for holding the seminar. It was great to have some people around and even hear some questions from you. I hope we could answer them by satisfaction to you. Otherwise, as I said, we are open to receive your emails later on. And let me wish you all a nice afternoon, morning, or night, wherever you are tuning to. And thank you for inviting us.
Thank you.